Please join me in welcoming Mr. Amber Rastogi.
I think you should be able to see my screen, right?
Yes, sir.
Okay. Yeah, let's get started. So I'm going to talk about some of the case studies for elastic data ingestion. This is from one of the largest trading clusters that exist today. Uh, Most of the information that I'm sharing here is a reference point that can be used by anyone to improve their system, existing systems, or to create a new system. Uh, so I would want to give a brief context before we deep dive into the topic. So when we talk about machine learning and training, it generally is divided into a few different categories. The major decomposition can be thought of as online training and offline training. Offline training is when you have a huge amount of data and you basically run trainers on them. You gather the output, and then you can use that to perform the inference later on. On the other side, online training is when the data is streaming at the moment and you have to capture all the information that you can. You don't have a lot of time to basically wait on that data. That data is just flowing through. One of the important models that are used in the industry today, those are called click-through rate models. They generally are used by social media companies to figure out how their advertisements are performing, what is the conversion rate, and how they can improve it. As you can see from here, like a lot of information from all the clients is just fed into a giant distributed events pipeline, which captures all the events. Some enrichment, if needed, is performed, and they finally send the data to the trainers. Like the goal is to send the data to these GPU trainers, which are very costly, as fast as possible. In between, somewhere, are these data reading and data pre-processing pipelines. And those pre-processing pipelines are the one that we are going to talk about today. Now, what is the major challenge here for the online trading when the data is coming in the real time? Is the traffic is not static, like it is bursty throughout the day. As you can imagine, right? In India, in morning time, the traffic is slow. Afternoon, it peaks, and evenings, it increases again, while at the night, it is slow. So the data volume, it has a peak and a slow on a daily basis. However, during a longer period of time, we can imagine that the data volume is constantly increasing. It brings us into the failure modes that for the readers, which are supposed to read all the data and pre-process it, either you are going to under-provision them, which means that you are not able to read all the data, or you are slowing down, or you are going to over-provision them. Over-provisioning is going to cost you more because you spend a lot of money and now you are not able to utilize your fleet. The third option that comes generally is tuning. But if you go for manual tuning, like, hey, someone is manually adjusting the number of readers all the time, that is not going to scale. All of these results into one of these problems. Like either the data is too stale, data staleness, or you end up losing the data because, hey, you are not able to ingest all the data which is coming in the real time. Or finally, if you over provision, then yeah, it's an inefficient CPU as well as GPU utilization, which is going to cost you a lot of money. The impact which is most dreaded in the industry is data loss. Uh, Data is equal to money in the industry. And if you are losing your data because, hey, you are not able to consume it at the rate, then you are silently losing your money. And the problem with online training is no one is going to give you a signal that, hey, you are actually losing the data. Your model quality is going to just keep on degrading over a period of time. And maybe it's not degrading, but not improving as well. So these signals are pretty hard to get. And when you find about that later on, there is no way you can go back and fix it because the money is already lost. So what's the solution? Like elastic data ingestion. So that's a no-brainer that we just need to be elastic during our data ingestion and data pre-processing. The goal would be to, hey, we want to keep the data as fresh as possible. Means as soon as the data is fed into our pipeline, we are just reading it. And we want to maximize our GPU and CPU utilizations because they cost money and we don't want to waste any of those time. As well as we have to remove the human intervention from any of the decision making. You don't want someone to wake up at 3 a.m. just to tune the number of readers. Generally, the design decisions that we rely upon is first, we need to have a very explicit signal on the backlog that, hey, how do we know that we are not able to keep up? It has to be a single metrics so that someone can take a decision on it in an automated way. One of the best metrics that I have came across is data age. So you fed the data into the pipeline and now you are reading it. You can calculate the diff and that tells you the data age. It is a very simple metrics, but you can completely rely upon it and make decisions based upon it. If the data age is beyond a certain point, let's say 30 minutes, you know that you are lagging. So that could be a time where you take decisions that, hey, I want to increase the number of readers. Uh, we also want to separate the durability from data reading. We don't want to depend upon, hey, if I'm not able to read the data in the real time, the data is completely lost. So that is generally one of the design principles that, hey, if you want to ensure that data is always durable, like I can come back 7 days later and still read the data. And it also exposes gaps into why the static configuration is bad. Because what is the optimal reader count? This is not a constant. It depends based upon the data volume at this point. Maybe you have a hardware issue. Maybe there is something bad with the network. That is also going to affect your reader count. So this is not a static value that you can configure. So whenever there is a real world problem, whenever you are running it at scale, something is always going to come and cause issues. So your system has to be prepared to change it, to change the reader count dynamically. One of the design principles that are generally used to solve this kind of problem is separating your control plane and data plane as any other application and keep monitoring your data age at any given time. If you keep monitoring the health of the system, then you can take decisions that, hey, I want to increase the number of readers, or maybe I don't have that much of the backlog and now I can back off because backing off is also needed, else you are just wasting money. So this is an elastic ingestion design that can be used and adapted to various use cases. This is your incoming data pipeline. These are your readers. We keep on monitoring the data age and keep publishing the data age, which can be ingested by a control plane. That control plane, based upon the data age, can make a decision that, hey, we are lagging 30 minutes. So it's time to increase the number of readers, or we have caught up with all the peaks. So it's time to get rid of some of the readers. It can calculate, hey, what is the next number of readers I need based upon whatever SLO have been configured. Then it can send a signal to rescheduler that, hey, please increase the number of readers or decrease the number of readers. And whatever application is handling your container allocation can take decisions. Very simple design. The design principle here just wants to expose few of the important subtleties, which is it has to be a continuous loop. It has to be a self-feeding loop. Generally, we do it epoch based that, hey, an epoch is 5 minutes. Every 5 minutes, we want to take a decision. Now, there are downsides of keeping it as low as 5 minutes, uh, which is, hey, maybe it's a very temporary peak in the data volume. Then you keep on making a lot of container allocations at any given time. And higher the frequency of container allocations, more delay you are going to cause to the system. It can cause some delays there because every time you increase the number of containers or you decrease the number of containers, you may have to reconfigure your data reading pipeline. There is some partitioning which is giving the information, hey, which reader is going to read what part of the data. And if you keep on resizing a lot, that keeps on changing, that may actually cause some issues. So these are some of the considerations that have to be taken in account based upon your workload that, hey, how frequently I want to make changes. How much changes do I want to make at any given time? Maybe you want to add 10 containers at a time as a step interval, or you want to only add 5 containers. Now, depending upon your requirement, depending upon how much capacity you have, you might want to tune that and take decisions based upon that. Similarly, your SLO. SLO is very highly contextual. You only you know that what is the SLO for your application. Maybe you can tolerate a 30-minute delay and maybe it doesn't affect you. Or maybe even 5-minute delay is very significant for your use case. So depending upon all those factors, some tuning is always needed. But this diagram shows you easy to apply system that you can just apply to your use case um, and take the advantage of it. So these are some of the real impact that I have seen using this approach. Uh, Generally, there is a GPU idle state or a CPU idle state in case your readers are not tuned correctly. Uh, GPUs are highly expensive. So any time loss in the utilization of GPUs is very costly. Uh, and if you don't have elasticity in your reader pools, then there is the other side of it that, hey, you just over provision. That means that your CPU is not utilized to its potential. That again is going to cost you money. So in the industry, in some of the places, I have seen that up to 20% of utilization in GPU with almost none data loss has been achieved using these models. If you can tune your design correctly, then you can achieve this. So one of the major impact that I have seen is reduction in data staleness. So data staleness is also one of the issues. Imagine you log on to some social media, for example, let's say Facebook. You click onto something and you get an advertisement based upon that 2 days later. Well, that is not going to be that impressive. You want the advertisement to be there in, let's say, an hour or in 10 minutes. That is what going to give you the ads money because that's is going to lead the conversion. So data staleness is very important for the industry. And by correctly tuning your system or having an automated tuner to tune the system, you can reduce the data staleness. Similarly, data loss. Data loss is directly causing you to lose money. GPUs are highly expensive, so any time that you are letting them sit idle and just eat up energy is causing money. So we have to be mindful about all of these things, and we want to ensure that we get the maximum utilization of resources. So some of the key takeaways here, generally we think about training and machine learning as, hey, GPUs and trainers, they are the main scalability challenges. Sometimes they are not. Sometimes it's just the data volume and how you ingest the data becomes the real key bottleneck in the system. If you are statically provisioning, then you are already flawed. It may give you a good start, but it's not going to work. You have to use elasticity in your system. Generally, there are a lot of systems that can provide you with dynamic scaling or elasticity, in other words, automatically. But even there, you have to be mindful about, hey, when do I scale up? When do I scale down? A lot of factors can affect it. Depending upon how much budget you have, how much resources you have, and you have to pre-plan for that. Maybe you want to increase your resources in a particular region where, hey, you depend upon AWS, but AWS does not have resource in that region. What do you do then? So these are some of the things that you have to think about when designing a large-scale system. Um, yeah, so if you make your system to be elastic, uh, then it can help you handle all these use cases. Generally, elasticity is thought about as an afterthought. That, hey, once my system is up and running, then I'm going to add elasticity to it. I think that is okay, but you have to be mindful about all the design decisions that you are making, all the schema changes that you probably need to make the system elastic. you should be thinking about that from day one. Else, if you think about it 6 months down the line, it might be too late for your system to adapt to the new design. Uh, yeah, that's all I had. Uh, if there are any questions, I'll be more than happy to answer.
Thank you, Mr. Amber Rastogi, for such a valuable keynote. If any participant has any question, they can raise their hand.
Okay, then. Seems like no questions.